Today we're going to look at solving some more trig equations. We've already started with this a little bit, and we know that the first thing that we want to do is to isolate the trig expression. So in this case, where we are solving secant x plus the square root of 2 equals 0, I'm going to subtract over the square root of 2 and get that secant x is equal to negative square root of 2. Now we could try to think about secant and think about the different values for secant, but it's a lot easier for us to think about cosine, remembering that secant is the reciprocal of cosine. I could rewrite secant and then take the reciprocal of both sides and turn this into a cosine equation of cosine of x equals negative 1 divided by the square root of 2. You may not quite recognize that as one of our special angle ratios, but if you rationalize that expression, you would get negative square root of 2 divided by 2, and that is one of our special angles that we know, one of the ratios for a special angle that we know. We'll go off to the side then, draw our circle, and think about what's going on. Square root of 2 divided by 2 is about 0.707, so not quite 3/4. And I need it to be negative. Cosine is the x-coordinate on our unit circle wrapping function. So drawing that, I should see that I'm of course talking about pi-fourths type angles. And specifically, we have the one at 3 pi-fourths and the one at 5 pi-fourths. So giving all solutions, I know that one set of solutions is x equals 3 pi-fourths plus any full circle away from that, so plus 2 pi k. But another set of solutions is when x starts at 5 pi-fourths and then you add any full circle from there. And so our main point here is that to solve equations with secant or cosecant, instead rewrite them using sine or cosine. With tangent and cotangent, we have a little bit different situation because we can't just break it down into sine and cosine. We still want to isolate the trig expression. So here, where cotangent squared x minus 3 equals 0, I'm going to first move over the 3, get cotangent squared x equals 3, and then take the square root, which says that cotangent of x is equal to plus or minus the square root of 3. If I try to think of that as a fraction and say that cotangent is cosine divided by sine, we already saw previously that you cannot just take the other side and pull it apart as the numerator being cosine and the denominator being sine. Doesn't make any sense. Instead, you'd simply have to understand what some of the special angle ratios are for tangent and cotangent, which is what I have developed over here. So in this situation where we have the square root of 3, we're looking here at this scenario, which means that the numerator came from square root of 3 divided by 2, and the denominator came from a half. So we'd be looking on our circle where the numerator of cotangent, which is cosine, needs to be the square root of 3 divided by 2, and sine, which is the denominator of cotangent, needs to be a half. So we have one of these four possible situations here. So we've got a half for the sine, we've got square root of 3 divided by 2 for the cosine, but because of the plus or minus, it could be any one of these four situations. I could have a positive square root of 3 divided by 2 divided by a positive 1/2. I could have a positive square root of 3 divided by 2 divided by a negative 1/2, etc. But the point is, the cosine has to be square root of 3 divided by 2 in length, and the sine has to be 1/2 in length in order to get this scenario here for cotangent. So my angles in this case are pi-6 And then from pi 6, like we saw yesterday, you could add any multiple of pi. So I get pi 6 plus pi k. And then the other set of answers that are coming up here because of the plus or minus square root of 3 is 5 pi 6 plus pi k, again where k is an element of the integers. Don't forget that if the text then asks you to solve it on a specific interval, such as the interval from 0 to 2 pi, you would want to write all the solutions first, like I just did, and then you would come down at the bottom and say on 0 to 2 pi. They're using an open interval there in the textbook. And then you would give the answers that are on 0 to 2 pi, which is actually all four of the ones we've drawn. So x is pi 6, x is 5 pi 6, x is 7 pi 6, and x is 11 pi 6. In our next example, we see that we have a couple of different trig functions mixed together. One suggestion that will sometimes work in this situation is to rewrite tangent, cotangent, secant, or cosecant using the definitions. And so here I'd get 4 cosine of x minus 1 divided by cosine of x is equal to 0. At this point, we see that we have an equation with a fraction in it, and we know that the best way to deal with equations that have fractions is to clear them out by multiplying through by the LCD of any of the fractions. Here, the only denominator we have is cosine, so we're going to multiply both sides of the equation by cosine x. Don't forget that we need to distribute that to all three of the terms that we see in that equation, which results in 4 cosine squared x minus 1 is equal to 0. So now we've gotten it down to just one trig function, and we can continue with the process that we've talked about before, isolating the trig expression, and that leads us to cosine of x is equal to plus or minus 1/2. So of course we'll go over and think about our circle here, where cosine, the x coordinate, is 1/2, or negative 1/2, and drawing that situation fairly decently, we notice that we're talking about pi thirds. And so our set of solutions are x equals pi thirds plus, and again in this case we have that unique situation of being able to just add pi to get to the next angle over here and the next angle over here for that set. So we've gotten these two angles taken care of in this situation. Now we need the other set of angles, which start at 2 pi thirds, and again add pi k, where k is an integer. So this situation of being able to add pi k rather than 2 pi k was because of the plus or minus that we got here, just like we did in the first example. Typically, you're only going to have two angles that you then are going to add 2 pi k. But little different situation here because of that plus or minus. In this situation, we haven't mixed different trig functions together, but we will notice that sine is raised to the first power, but it's also raised to the second power. I call this situation a quadratic-y type equation. It looks virtually like a quadratic equation, except in place of an x, we actually have a sine x. So like a quadratic equation, the first thing we're going to do, of course, is we're going to move everything over to one side and set it equal to 0. Now, for a lot of people, it may be really helpful at this point to make a replacement. For example, if I were to let a equal sine x, what I notice is that the equation I have really says 2a squared minus a minus 1 equals 0. And that's a quadratic equation that we should be able to solve, hopefully, with factoring. So I'll go ahead with this by using this replacement for sine x with an a. Because the leading coefficient here is not 1, remember that we multiply the leading coefficient and the constant together and then figure out how to decompose our middle term. We need two factors of -2 that will add to be the -1 that we have here in our middle term. That, of course, is -2 and 1. So now I'm able to decompose my middle term as a -2a plus an a minus a 1. So we get 2a squared minus 2a plus a minus 1 equals 0. And what I'm doing here, of course, is that factoring by decomposition, which then relies on factoring by grouping. On the a minus 1, the only common factor is a 1. And so finishing that out, I get 2a plus 1 times a minus 1 is equal to 0. But going back and replacing a with my sign, what that means is I actually have 2 sine x plus 1 times sine x minus 1 is equal to 0. If you can do that factoring without actually making the replacement with an a, then that's great. That would be awesome. You don't have to actually show this if you can do the factorization with the sign in there. But I just wanted to emphasize how it really just has the form of a quadratic, so we're going to use the same processes that we had used with a quadratic. Of course, the whole point of the factoring then was to use the zero product principle and break down into separate equations. So I get 2 sine x plus 1 equals 0. And sine x minus 1 is equal to 0. And now we have two simpler equations that we can solve using the processes we've talked about already. At this point, I've run out of room to work here, so I'm just going to continue on to the next page. We have those two simpler equations that we've created using the zero product principle, so I'll simply finish solving them the way we've been doing. This gives me sine x equals -1/2. This tells me that sine x is equal to 1. I will, of course, go to my circle and think about my situation here. Sine is a half. That means the y-coordinate on the wrapping function is, it's -1/2. Sine is -1/2 for this equation. Hitting the circle, that tells me that the angles I have are 7 pi 6 and 11 pi 6. We don't have that plus or minus. We don't have that other half of the situation going on like we've done in the others. So for the 7 pi 6, I then have to add 2 pi to get two other angles there. For the 11 pi 6, I'd have to add 2 pi to get to the other angles there. So my answers for this section are x equals 7 pi 6 plus 2 pi k, and x equals 11 pi 6 plus 2 pi k. However, I'm not finished because I have this other equation that I need to finish solving. So I really should go ahead and just think about one big bracket to include all of those. For sine x equals 1, that means that my y-coordinate needs to be a 1, and that only happens right here at the top. So that is pi halves, and then you would have to go a full circle away from that before you would hit again. And so these are my solutions to this equation. I just needed to treat it as if it were a quadratic first. Of course, I also may be asked to only do this on a certain interval, such as 0 to 2 pi, and I would just pick out the 7 pi 6, the 11 pi 6, and the pi halves as my answers, but put them in numerical order. In the last example, which I won't get time to finish, the one thing I do want to show you here is that you do have a replacement you can make for sine squared using the Pythagorean identity, which will allow you to put this all in terms of cosine.